And we're live. Do you ever wonder what it is that makes you feel motivated, amped up, focused, locked in to achieve that dream of yours or that goal or that task? Well, there's a very special molecule in our brain that's at the center of it all. But that's not it, because that little molecule, we're going to talk about it. It does so much more that you never even knew it did. So stay right with us. Don't go anywhere. We're going to be right back for today's episode of the Rad and Norty Show. And we're live. All right. Another week of the Rad and Norty Show. Josh, how you doing? How you looking? I got my cup of tea. I'm ready to get into it this week.
Good, man. We had some wild weather here in Chicago. I don't know if you got hit with those nasty storms, but the weather's fluctuating. The wind brewed up. Thankfully, no crazy winds in the city of Chicago itself, but the suburbs got hammered. So,
yeah, my buddy who's out, I guess, I think like northwest of you in Illinois, sent me a picture like of his backyard, literally tornado.
Oh yeah,
like off in the distance. Like, I mean, it was probably like a mile away. It was not like literally
I think
10 feet away.
If I remember,
you're taking a picture of a tornado, like that. You're not messing around.
Yeah, if I remember correctly, he's way up north. He's probably closer to like Beloit, Rockford, that area than I am, and like that's the area that got hit really bad.
Yeah, that's why we had our first veteran group on Friday. But he wasn't able to make it because like literally he's like the tornado came through. There's no internet. There's nothing. Like, that's crazy, man.
It's gnarly. So
I know. I remember being a kid watching that movie Twister. I mean, I was probably young. I mean, not that old, and I remember just being like totally freaked, man.
Well, when I was really young and I was living in a suburb, Romeoville, at least I think that's where I was living at the time, and staying at a friend's house, and his dad's like, there's a tornado touching down. We're going to go look for it. And like, I couldn't see the funnel. Right. Like the winds were clearly forming. It was just crazy. Like that's a fond memory was going to chase tornadoes. And then I saw Twister.
Is it true you hide under a bridge that the tornado has to pass over you, or is that all a lie? You just get sucked out from underneath the bridge?
I have no idea. I don't want to test that. I don't want to find out, but I don't want to be close enough to a tornado to have to hide under a bridge.
There's some crazy YouTube videos out there, like people just seeing tornadoes like rip through like their front yard and stuff.
It ripped through like Tennessee or somewhere and like demolished, or maybe it was, I don't remember where it was. I thought it was Tennessee, like ripped through an entire town.
No, it was right around the same time. I think it was Little Rock, Arkansas, maybe.
That sounds right. Yeah,
I think it was like right around the same time that Tennessee, the Nashville shooting happened. So it was like, I remember the headlines were like Nashville shooting in Little Rock, Arkansas, torn apart by a twister or something like that. Anyway.
Yeah. Anywho,
enough catching up. I mean, no real notable world events on my end. We are going. Our family will, sadly be having a funeral for a lost loved one tomorrow. But other than that, no real major life events.
My condolences, and I'm sure our viewers, send their condolences as well. It's never a fun time.
No, it's not. But, when we do think about these things, I mean, obviously, I think my emotional reaction to all this kind of stuff, admittedly, is a little blunted as someone who takes care of patients that, dying is. I work in a specialty where dying is not an uncommon event, unfortunately. And so you kind of do become a little numb to these things. But, I definitely feel for the family and, how hard it is on many of them.
I'm very similar. I'm not a doctor, as everybody knows, not a Dr. Norty over here, but experienced a ton of, like, everybody in my family's dead for the most part. And so like I've just become like,
everyone in your family's dead.
Pretty much.
That's a blunt way to put it, my friend.
And like that's why I've just become almost like cold or numb. But like I feel bad for families, everybody affected. Like it's not a good time, but that's my coping mechanism as well.
Yeah. And also, having seen a wide spectrum, I'm so used to, the tragic deaths, somebody's in a trauma, hit by a car, massive brain bleed in somebody that, is really unexpected. I think in many ways that has given me an appreciation for when a loved one passes at a later point in their life. They've, lived a long life and their passing is not unexpected. How important or in many ways lucky a lot of families are when they get that time. I'm very grateful for the way that my grandmother passed, not I guess less than a year ago now. Or no, it's a little over a year. I think this past November was a year, if I'm not mistaken. October, November, I think was a year. So it was fairly recent in the grand scheme of life. But
And that's what I found out too, is knowing and not having that unexpected, experience both, and the knowing and getting to really cherish the time with someone who is unfortunately going to pass. You become very grateful for those type of things. It really does put things in perspective. And like I always highlight that as like, well, you got to take the wins where you can get them, right? And at least appreciate what you've got. And
I remember when very early on in my clinical training, there was literally it must have been one of my second month, even as early as my second month. There was a man who was brought in, just basically woke up at 3:00 in the morning, bled massively into his brain and died. He wasn't a young guy, right? But he was not previously sick. It was not like a declining in his health to the point where like, oh, we finally reached this moment. And even though, he was married and literally just went to bed and woke his wife up, I think like 2:00 or so, to say he had a headache. And then basically 3:00, she like rolls over and he's like non-responsive. I mean, literally just something about that suddenness. Like, even though they're an older couple, like they knew like, end of life was somewhere in the tangible future.
You don't want it to, right? You don't want to blink and have it happen.
Yeah, literally just blink and your, loved one of probably 50, 60 years, I'm sure they were married, just gone. I mean, that's the type of thing, like that's really hard, even as a physician, to see patients when that happens. So, when you get that sort of slow building towards the end of life, I think that those experiences have made me more appreciative of the perspective of a sort of slower approach to end of life for the patients that do get, and families who do get that experience. But anyway, enough about that. Obviously we're just catching up on life events. Let's get into the actual topic of discussion for this week, which
a pretty dope topic.
Yeah. Okay. All right.
See what I did there? See what I did?
Yeah. Yep. Okay. Are you? We're not talking about doping. That is something entirely different. We're talking about dopamine, which I think initially when we discussed the topic for this show, we had some ideas of the direction we wanted to go in. And the more I really was sort of re-educating myself, right? A lot of this stuff is like, oh, learn this in the past, but you got to spend time and sort of refresh your knowledge on these things before the show. Dopamine is such a broadly functioning molecule in the brain that I thought a good direction for tonight's scope of the show was to really take a step back and kind of talk about all these different things to realize like there's this one molecule in your brain and it does so much. So obviously over the course of the show, I think we'll get into all the various different things that dopamine does in the brain. But what are some of the things that in your sort of non-scientist world, you think, I guess the fact is you say the word dopamine, that means something to you, right?
Yeah. And
that's incredible when you really think about it.
Yeah. And you associate that with like, well, at least it's again, limited knowledge, right? When you hear the words dopamine, you're like, oh, you get a hit of dopamine, you're happy, you're ecstatic, you're
But the
motivated. It's
fact
like a
that is even like
yeah.
normal knowledge to the public is actually kind of amazing,
Mhm.
right? Like, what if I was like, oh, what about the gamma aminobutyric acid levels in your brain? Like, what does that mean to you?
I couldn't even repeat what you just said.
I mean, I probably mispronounced it, frankly, because it's
I
one of
heard
those
gamma.
like
I
it's
assume
a
that's
very common thing to like neurotransmitter to like read about. But the thing is, it's like one, we abbreviate it, so very few times you actually have it written out. We abbreviate it as GABA, GABA, and when it is written out, you kind of like have read through it so many times. It's like your eyes read
just,
over the word and you know what it's talking about, but you're not really pronouncing it.
and
So
you're not even remembering exactly
I
what
mean,
it is, right?
yeah,
Yeah.
gamma aminobutyric acid. Anyway, but it's like as a scientist, if I say that, that means nothing to you, right? No impact,
Yeah.
no idea. Is my assumption,
Right. And
right?
probably
You go out
zero
in
to
the
like
general
most
public,
of the general public probably
yeah.
have no clue what that means.
But
Yeah.
if you go to someone on the street and you're like, "Oh man, let me get a hit of that dopamine," right? Means something to
Mhm.
people. Like that's incredible when you really think about it. That it has like almost like a
Street cred. It's got
yeah,
street cred.
like it's a neurotransmitter with street cred.
Yep.
I mean, what other neurotransmitters have street cred?
Not many.
Maybe serotonin.
Serotonin's one.
Maybe uh, uh epinephrine.
Yep, I know I've heard that one.
I
Couldn't
mean,
tell you what
people
it
probably,
does.
I mean, colloquially, they might not necessarily understand exactly what you mean, but then you're like epi, and they're like, "Oh, I've heard of epi."
Yeah.
So, I mean, outside of that, I mean, I can't. I mean, neurotransmitters having street cred. I mean, hey, it's cool to be a neuroscientist, I
Yep.
guess.
Yep. When dopamine is involved, it's cool. But that's like, that's what I think of it as. When you outlined the fact that it's got many applications in the brain, different functions, and it's doing all of this work, like I think that's going to be a cool thing to unpack and have a
Yeah.
better understanding for people that associate it with, oh yeah, like feelings, boom,
Mm-hmm.
dopamine, good stuff.
We're going to get down that line of the conversation. While we do, welcome to everyone in the chat. You've kind of gotten a good sense of what we're talking about tonight. Go ahead. Tell us in the chat. Obviously, give us a thumbs up, wave hello. It's always nice to see the audience out there in the chat. If you have questions, send them along. We'll just kind of stop the conversation and answer questions as they come. Related, unrelated, doesn't matter. We're here to have a good time. And, tell us, what does dopamine do? That's the question, right? I'm kind of curious to hear what other people have to say. There may be very, scientists out there, non-scientists out there. So I kind of want to see the spectrum of like, what does the general audience think dopamine does for you?
Let's see how deep that street cred runs.
Yeah, let's see
dopamine.
exactly. So anyway, let's get back to your perspective on this.
Mm-hmm.
You mentioned, dopamine is,
it's the chemical that goes off when something good is happening, right? Like almost a reward. You get hit with dopamine spike, you're feeling good, you're motivated, you want more of it, right? Like you want to do whatever it is whatever you did to get that dopamine, you want to be able to replicate it and do it again, get that good feeling, right?
So I would agree that's the most common understanding of the general public of what dopamine is. But really it's actually, so physically as a molecule, it's actually not, it's sort of a derivative of epinephrine. And so norepinephrine, epinephrine, and dopamine, they're all sort of not the same molecule, but it's sort of like the same molecule modified in different ways. So it's like a fundamental molecule in the brain, really. It does all kinds of things. So what you're describing, I think, is actually what's come to be known. Let me get the reward prediction error hypothesis of dopamine, right? And the idea is that dopamine really, I mean, it obviously does tons of other things, right? What we're talking about right now is like purely the cardinal understanding of what dopamine is. And then obviously we can branch off and talk about all the other things that, frankly, you probably don't even realize dopamine's playing a role in, right? But what it does is basically, in many ways, it couples things, right? It allows the brain to say, oh, I did this action, and that action resulted in a reward. I like that. And so dopamine being involved in that process allows the brain to encode or to learn that doing that activity yields a positive reward. And so to get that reward, I want to repeat that activity. So what it's really doing is encoding activity in the brain, into the brain, right? And you can couple that to other things. And this comes down to, I think, a really cool idea of neuroscience. I just, in layman's terms, we'd always say like things that fire together, wire together. And dopamine facilitates that process, right? So if you have an action, that action yields a reward. But let's say that you want to encourage someone to do, well, let's break it down a little bit more, discreetly, right? You have action A. Action A, keep my hands on the screen. Action A yields a reward. Screen's not very big when we're next to each other. Action A yields a reward. Action B is what we really want them to do, right? Mm-hmm. So what you can do is you can couple action A with action B. That way the reward that comes from action A wires to the action B.
Okay.
Maybe drawing a diagram would be a better way.
Might be a little bit better.
I wish there was a way we could just like turn on the ability to just draw.
Like
maybe we could do like a whiteboard. Actually,
that's what I'm thinking. There's got to be a whiteboard.
Google will help us out here.
Just do Microsoft Paint. Can you do Microsoft Paint?
I think there's a board on a Jamboard. Is that what it's called?
Yeah, I've heard of a Jamboard before.
I think this is Google. Tap to create one.
I can fire up Microsoft Paint. We can see how good my drawing skills are.
If you want to do that, we could try that. I'm trying to. Oh, here we go. I click this button, I think, and I can just draw now, right?
I like where this is going.
Okay, here we go. There we go. I got it.
Are we cooking? All right.
Oh yeah, we're cooking with gas, my friend.
Ooh, I'm feeling some dopamine
do some drawing here. Let's pull it up. Window. Screen 2. Boom. All right. Here we go. We good? Can you see?
I can see. You're doing it.
I don't have a pen, so I'm not actually drawing with I'm just drawing with my mouse. Okay, so we have A. We'll call this action. We'll call A for action, and then we'll give it a little subscript A. Right? Action A, action B. Right? Action A gives the reward. Right? Let's say this is like, we can use like the traditional Pavlovian experiments, right? Pavlov and his dogs, right? Action A is basically presenting, I don't want to write this out, but let's say action A is like presenting the dog with food. Is there a way I can stick in like quick text box here? Okay, food. Present food. Right? It's like a pretty simple idea, right? You present food to the dog, and what is the result? Well, it causes the dog drools, right? These are like the typical Pavlovian experiments that were done, right? This whole sequence pretty straightforward, right?
Yep.
You present a thing of food to a dog, the dog drools. Now, in Pavlov's experiments, right, he basically then took a bell ring, like he literally took a bell and would ring it, right? And initially what he did is he coupled these two things. So you'd ring the bell, give the dogs food. What happens? The dog drools. And you do that over and over and over again. What's happening is these action A and action B, or is my mouse like all over the screen, or is it just mine?
No, it's kind of flickering, but it's fine.
Yeah, I was gonna say it's showing me flickering, so I'll try not to just mouse around. So action A and action B, you present them together. Eventually what will happen is they'll kind of wire together, and action B will be wired to the result.
Yep. So even when you remove action A and you just ring the bell, you still get the same result, right? Like that was Pavlov's.
Yeah. So that was like the very basic example, but then that can extend to many other things, right?
Mhm.
You can couple other behaviors that you want to ingrain with other actions, and dopamine basically helps reinforce the neural circuitry that promotes these behaviors.
So what's going off? Like what is happening with dopamine in these scenarios, right? Like what is causing it to be able to rewire things? What's happening in the first place when you're getting the reward? I think that's a good place to start. So when you have action A, you're presenting me with food. I drool. What's happening? What's happening with dopamine when that occurs? Because I guess
what is the actual
dopamine's role in this? Like what happens in the brain with dopamine? Like how is dopamine associated to this?
You're kind of asking like what's the biology of the concept firing together, wiring together?
Right. Yeah.
So basically the strength of your circuitry is going to be primarily, it's without like painting a really complex picture of neuroscience, right? When a nerve reaches out and touches another nerve, right? It's not like a one-to-one connection, right? It's almost like a nerve can reach out and touch multiple nerves.
Tons of stuff.
It can reach out and touch a nerve in multiple spots. It's a very, its ability to actually transmit a signal from one neuron to another is a complex situation. So what happens is what dopamine, I mean, there's a couple different molecular pathways that dopamine can modify those connections, right?
So dopamine's the modifier. It's not actually like the connection. That's why I'm just
primarily, dopamine is modifying this neural circuitry, and there's actually a lot more information there's a lot more interest in the idea of how dopamine couples with other neurotransmitters, in the sense that it's not like a neuron fires, it dumps a bunch of dopamine, and dopamine goes out and has this effect. But in fact, dopamine gets released along with glutamate or along with GABA. And together they do different things in different locations of the brain, right? Because it's not as simple as like put gasoline in the engine, pull the ripcord, and the engine runs, right? It's not like you put it in and something comes out.
Put it in, shake it around.
All right. There's like, not only is it like, well, did you put it in, imagine like an engine that has like 15,000 different gas caps, and you can put the same gasoline in a different gas cap and it will power the engine in a different way. Not that this is possible, but theoretically, like imagine that engine basically like that the part of the engine and the drivetrain that's connected, is different depending on like what gas cap you pour the same gasoline in, right? So there's sort of like a spatial relationship, right? It's not just what, but it's where in the brain. And then it's also what, where, and like what other things is it being coupled with? And then what, where, what other things is it being coupled with, and over what period of time?
So I've got a question for you, and this is probably going to be a dumb question, but I think you're used to that by now. Would you classify dopamine as like a chemical in the brain? Because when you think of somebody having like maybe a chemical
impact, it's a monoamine. So a chemical in the
I'm trying to like break it down to like the simplest form that I can.
A monoamine would be Yeah, I mean, it would be considered a chemical, right?
Okay.
Because an amine or an amine is it's an organic molecule, not macromolecule, to my understanding. Macromolecules are primarily, amino acids, carbohydrates. There's like four major macro. I'm very far removed from my molecular biology. Macromolecules,
Well, that's
amino
what I'm thinking.
acids,
I think of dopamine as the
carbohydrates, nucleic acid. Yeah, so it wouldn't be considered classified. It would be considered a chemical, not a macromolecule.
okay. And well, that's like because that's what I think of, right? You think of this chemical going off in your brain and something when something good happens. You think of like a dopamine like getting poured, like you're saying with the gasoline. And what you're saying is it's not just the dopamine doing that, it's how it's paired with other things and where it's located, right? In the brain.
Yeah,
More or less. I know that's probably oversimplified.
no, I mean it's a pretty good way to put it.
Okay.
But that's how you can take a single molecule
Mhm.
and make it do so many different things because there's so many factors other than just the molecule itself, right? It's almost like
You broke up big.
imagine what's that?
You broke up for a
Hang on.
second
My
there. You were
oh,
cutting in
okay.
and out.
I'm
You're
sorry
back now.
about that.
No, you're good.
I'm back now. We probably just had a little dip in the internet. It's like imagine when you talk about neurotransmitters, right?
Mhm.
A neurotransmitter is just a key.
Mhm.
And it's a key that can unlock many different locks. Right? Now imagine you have
I think we used this analogy last week even,
I
or
think
maybe
we've
2
definitely
weeks
used it
ago.
before, right?
It's recent. It's recent enough for me to
Yeah,
remember
I mean
and say
imagine you've got a keychain. I mean, imagine neurotransmitters, right? Imagine you got a keychain of, 5, 6, 7 different major keys that unlock a lot of different doors, but every door you unlock, there's something different behind it.
that. Mhm.
Right? Different location, different whatever. And then it's also one, a neuron firing, it dumps vesicles of the neurotransmitter. A vesicle is like a small package, right? You have to
Mhm.
think of like the end of a neuron is like, imagine the end of a neuron is like the bottom of a Christmas tree. There's tons of packages just bundled up under the Christmas tree. And then the neuron fires, and all of a sudden, that's like what it does is it basically like shoots the packages out from underneath the Christmas tree. The packages burst open in midair, and the neurotransmitter that's inside the package is all of a sudden just released into the air. Right? Obviously, it's not the air; it's what we call the synaptic cleft, which is the space between neurons. Right? But now this basically you're taking a packaged up a vesicle of neurotransmitter, releasing it out into the synaptic cleft, or in our analogy, the air. And then it basically dissolves, floats through the air until it just happens to land on a key that's willing to receive it on the other side, which is, attached to another neuron. Or it could just get scooped up and recycled. It may not even the key may not even go into the lock, right? It's a law of large numbers, right? Just spray and pray.
Spray and pray. Hope you
Right?
hit something you like and have fun.
If you spray more,
Mhm.
the probabilities are in your favor, right? That you're going to unlock more keys, right? And so if you unlock 5 keys or 5 doors, because 5 keys landed, versus unlocking a million doors because you had a huge dump of neurotransmitter, the effect that it's going to have on the receiving neurons is going to be drastically higher compared to the former scenario. And so that's another factor, is not even just what's being released, where it's being released, how much of it's being released, what type of door is being opened, how many of those doors are being opened, and on what neuron are the doors being opened on.
And it is incredible when you think of it that way, like how it all works together and eventually finds the right place and has a normalized effect, right? When things like that are going on. Now, I asked about it being classified as a chemical and people possibly having a chemical imbalance or lacking specific chemicals.
Yeah.
Is dopamine something that people can lack or produce less of? Like, how would that work?
So that's a great question. I think the general answer is yes,
Mhm.
but I don't think it's as simple as like you can't like measure someone's dopamine levels,
Right.
right? I mean, there's like the dopamine hypothesis of ADHD. That the idea is ADHD clinically is generally people, with the low dopamine levels, right? Does that mean it's truly low dopamine levels? Or is it maybe that they don't have as many receptors to receive the dopamine? So it's like you can flood their brains with dopamine, but it's like,
It's not going to do anything because it's the receptors picking it up that are causing the issue, not necessarily
exactly,
a
right? In
lack
which case, maybe
of.
then you need, like, let's say, because everything's a probability, right?
Mhm.
Let's say there's 100. Normally, let's say there's a million doors to be open and you spray 5 keys out into the abyss. There's a chance that all 5 of those keys are going to open a door,
Mhm.
right? If you have a million doors and you spray a million keys out into the abyss, there's a high chance that way more than 5 doors are going to be open, right? So you can sort of see how,
But
let's
there's
call
also
that would be like let's call that like the normal scenario.
right.
Right now, take a scenario where like you have 5 doors. What's the chances that you spray 5 keys out into the abyss? They're going to open 5 doors. Very low, right? Now you spray a million molecules out into the abyss. What's going to happen? Well, you just flooded the field with dopamine. You're probably going to open all 5 of those doors. Are opening all 5 of those doors going to have the desired effect? It's going to be
Only 5.
better. It's going to be a better effect than just throwing 5 keys out there.
Yeah.
But the reality of the situation is, even though you're flooding it with dopamine, you're still going to have a blunted response compared to maybe the normal scenario. And so there's a lot of reasons why you could have like low dopamine, but it's not as simple as just pump the brain full of dopamine.
Right.
But ADHD is generally the hypothesis is it's a low dopamine effect, whether it's from truly low dopamine or from, probably.
Lack.
And these things, I think a lot of these things tend to be more receptor mediated
Mhm.
like neurotransmitter mediated. That's my kind of, I would say, sense of the matter. Like I said, I have not like grossly researched every single neurotransmitter or primary disease process that's primarily rooted in neurotransmitter.
Well,
But
again,
I think
this is the stuff that makes me so I get so curious around this because it starts to tap into that what makes people tick, right? Or what makes people have certain effects for whatever the case may be. And we can all be wired certainly different or have different amount of transmitters, different amount of receptors that do different things. Like this stuff is fascinating. Just getting a better understanding of how it works is cool to me. So, and that's like, I forgot what I was going to ask. I spaced out in the middle of
that's
my
all right.
sentence.
While
Yeah.
you think of your question, we'll take a quick pause. Welcome everybody to the show. We're talking about dopamine and the effects in the brain today. Although we are kind of just more generally talking about neurotransmitters right now and kind of the biology of neurotransmitters. If you're out there, you have any experience or no experience, don't worry. We hope you're enjoying the conversation. Let us know in the chat kind of what you think in terms of neurotransmitter related disease processes. Obviously, serotonin plays a big role in depression. There's primary leading hypotheses about dopamine and ADHD. Then there's obviously more concretely understood diseases like Parkinson's disease and its role, dopamine's role with Parkinson's disease. So anything you know or want to share, just go ahead and leave it in the chat. If you have questions, leave them in the chat and we'll answer them. But kind of going back to what you were saying, though, Josh, to kind of take it one step further, even blow your mind a little bit more, if you will. We've kind of used this like key and door, like locked door idea, right? But now you've got different types of doors in this sense, primarily what we call like 2 different types of doors, right? You have one door where it's like you open the door, it has a direct effect. right? Sort of like open the door and just, it triggers whatever it needs to trigger. Then you've got doors where, have you ever seen those crazy YouTube videos where those people make like those really complex like machines? And like there's this guy, I forget what they call them. They're like these really complex machines, and it'll like automate them like feeding him a sandwich.
No.
You've never seen these?
No.
I feel like they're very popular on YouTube.
I
See
don't.
if I can find one.
Yeah, if it's not video game related or sports related, or if I don't follow it, I probably don't go out and search for new things on YouTube.
Machine. We call it, I don't know. I'm sure if I type in, I feel like I've seen like a sandwich one a lot. Sandwich machine. Let's see what comes up.
When you said like build machine, I used to watch this guy solve puzzles that were like handcrafted. That's the craziest machine I could.
Yeah, it's something like that. Probably. Here, let me pull this. Probably have to fix the. Well, I pull that up. We got Kristen says, I'm thinking about all the dopaminergic pathways, studying psych and neuro for clerkships right now. Well, there you go. So there's a lot of dopaminergic pathways, right? It's one of the key neurotransmitters in the brain. And the thing that's interesting that I found is you learn about all the different individual dopaminergic pathways in the brain. And you sort of like, you'll learn about them over here, you'll learn about them over here, but you don't often like really pull them all together. And I think we're going to kind of take a step back and look at like all the effects of dopamine in a little bit. There's even outside the brain, dopamine does tons of stuff peripherally. So it's pretty wild. It affects a lot of different organ systems. Well, let me pull this up here. Have you ever seen like something like this? Let me skip the ad real quick. We don't need that. Actually, I don't even think we really needed the sound, but why won't it let me? Oh, skippable ad. But like these like machines people make. Oh yeah, this guy makes all kinds of crazy stuff. We'll speed it up. We don't need to watch this on.
Okay, I've seen stuff like this.
Yeah. So it's like imagine a receptor or like a door, right? Dopamine gets released, and then it opens up a door, and really all that door is doing is triggering this big giant cascade of events like this inside of the receiving cell, and causes some property of that cell to change. Right? Maybe it tells that cell, oh, I want you to produce more receptors on the other side of the cell for this other molecule. Right? And that's how you get things like firing together, wiring together. Right? You trigger these pathways where you basically, the release of dopamine is telling the receiving cell to stick more doors out on the other side for this totally other different molecule like glutamate or something. So then the receiving cell becomes more excitable. So it almost like wakes the receiving molecule up to be more receptive to a lower signal of something else. And so all of a sudden now you may become like, we'll just call it, we can turn this off. I don't think we need this anymore. Let's call like dopamine fires on neuron A, and neuron A's job is to tell you that I don't know, make your finger click faster when you're playing video games, right? You said you like to play video games, right? So neuron A's job is to make you click faster when you play video games. Now what happens is, like, if dopamine can influence neuron A, so that way glutamate, which excites neuron A, it tells neuron A to express more receptors for glutamate. So then when that glutamate gets showered on that receptor A, now your finger's firing faster. but it doesn't take more glutamate to increase that response. It makes that neuron more responsive to the same
Because
amount
of the
of
dopamine?
what's that?
You said because of the dopamine? It's then
Yeah.
almost like
This is a
hyper
theoretical
receptive
scenario.
to it?
Yeah, like dopamine can make that neuron because it's hyper receptive to its stimulus.
Hmm.
So now you don't need more stimulus. You don't need to pour more gas on the neuron, right? You get more RPMs, more horsepower from the same amount of input. That's one example.
That's fascinating.
The wheels are turning.
Yeah, they're just cranking away.
And that's why, I mean, this is where I think we've talked about like video game addictions before.
Right.
I think dopamine plays a big role in that because you'll get, and that's why things like winning, in many ways, probably the best way. It sounds stupid when you think about it, right? The best way to improve your motor function. So actually, hold on. Before I make this point, I'm going to make one other quick point, right? We've talked primarily about the reward of dopamine, the reward effect of dopamine, or what we call the reward prediction error, right? Dopamine's all about like, how well can you like basically you predict you're going to get an outcome, and then when you are right, you kind of get this little shot of dopamine. Does that make sense?
Yep.
So it reinforces the behavior that led you to predict the outcome. Kind of. It's a very simple way to put it. We've talked a lot about that. What we haven't really talked about is the motor effects. Dopamine plays a big role in movement. And that's why when you see patients with, the primary treatment for a patient with, say, Parkinson's disease, right? What's Parkinson's disease? Parkinson's disease has street cred.
Yeah. That's
what is Parkinson's disease to you? I'm I'm not quizzing you. I'm asking you, like, what's the street's perspective of Parkinson's disease?
And I don't want to sound too bad, but you shake, right? Like that's Parkinson's is.
Well, yes. I mean, admittedly,
that's what I think of.
That's what I thought for years. So actually, that's really more the Michael J. Fox Parkinson's disease. Because actually Parkinson's disease, you freeze. It's the inability to initiate movement.
Okay.
And the drugs that treat it help increase movement. Obviously, I don't understand Michael J. Fox's healthcare. I've never been a part of his healthcare. My understanding is because he's so proactive about treating, and he's such an advocate for advancements in Parkinson's disease. He's probably been a part of like many trials and things like that, where he's almost like over treated, and that's why I think he has so much uncontrollable movement.
Well, I feel like Muhammad Ali was very similar. Like I remember him walking and seeing like his hand shake.
So you can like a tremor is one thing.
That's what. Yeah.
Michael J. Fox, if you watch him, like he can't stop moving.
Gotcha.
Right? I mean, like think about like Michael J. Fox. Like he kind of is like
he's very like almost fidgety,
and he goes like this, and he's kind of like and then, like that's not really that's not textbook Parkinson's disease. I think that's largely extrapyramidal side effects of the medications that he's on.
Gotcha.
What's that?
It makes sense the way you described it, where it's actually like the limitation of movements. Because I think of Muhammad Ali, he's very slow, but his hand would tremor.
Yeah.
Like I have this picture in my mind where his hand is just shaking. He like can barely walk. Yeah.
So the typical like textbook. I mean, look, we got Kristen in the chat studying psych and neuro pathways. Right. What are some of the cardinal clinical indicators of Parkinson's disease? But they'll all primarily revolve around basically slowed, impaired, inability to initiate movement. And so the treatment is focused on activating movement, and the staple treatments for that are what we call levodopa carbidopa, which is basically synthetic dopamine. And the synthetic basically just floods the brain with dopamine because the disease is rooted in destruction of the dopaminergic neurons in the basal ganglia. And the basal ganglia is just, in simplest explanation, is just a central part of the brain that controls the initiation and termination of movement. So it's almost like a, what's the best way it's been explained to me? Almost like a toll, right? The brain's sending out signals to start and stop movement, but it has to go through the basal ganglia as a toll, where it actually, like, it will open and close the gates to actually allow cortical neurons from the motor strip. So, right, the motor part of the brain is trying to make your body move, but it has to go through the basal ganglia. The basal ganglia, based on dopaminergic input, will either allow those movements to proceed or it will block those movements from proceeding. And it's actually the very fine balance of the basal ganglia that allows us to have smooth movement, right? Think about driving a car.
Mm-hmm.
Imagine if you had a car with no gas a car with no brake and all gas. Think about like what it would be like really driving that car. It would be like, right? As you're kind of like step on the gas, take off the gas, step on the gas, take off the gas.
Right.
Now, obviously, we've engineered cars much better, right? But if you think about like, have you ever like driven a golf cart where it almost seems like as soon as you step on the gas, it like engages because it's an electric motor, not.
It's same with a Tesla. It's got like a.
I've never driven a Tesla. But...
Yeah, so it's when my buddy bought a Tesla, and like the first question they asked him is like, "Have you ever driven a golf cart?" Because it's very similar. You press on the gas as soon as you let off. If you completely release it, the car will just stop. It's almost like slamming on the brakes because you lose all go power.
Yeah, it's sort of
it's like degenerative braking, I think is what they call it.
It's kind of similar idea, right? It's like imagine like a really crappy golf cart. Yep. Sort of similar idea. Now imagine like the way that you would then turn those like really rigid movements into smooth movement would be like, now imagine you never really took your foot off the gas pedal, right? You can slam it and you can floor it and you can back off of it, but you never fully take your foot off the gas pedal, right? But eventually you're going to hit that point where you've relaxed your foot on the gas pedal enough without taking off all the pressure, and then you apply a little bit of brake, and that will bring you to a nice smooth stop. Now you can leave your foot stationary on the gas and then take your foot off the brake, and what's going to happen? You're going to start moving forward,
right?
And you're going to do it in a slow fashion as you ease off the brake.
Because it's smooth, not this rigid.
So imagine that like the cortex of the brain is like the gas pedal, the electric motor gas pedal, right? You never really fully take your foot off the pedal. You can relax it and you can depress it, but it's like always kind of engaged to some baseline level.
Right.
And then the basal ganglia kind of functions, the dopaminergic neurons of the basal ganglia kind of function as that application or release of the gas, or I'm sorry, of the brake, to allow these very rigid, jerky movements that the cortex of the brain wants to initiate, to turn them into like really slow and intentional and steady and, you know, functional human movements, right? And that's why you see very like rigid movement in someone with Parkinson's.
It's because you said it's the degeneration of that, or the breakdown.
Yeah, degeneration of the subthalamic nuclei, dopaminergic neurons of the subthalamic nucleus.
So is it
Kristen Worth? If you're out there, fact check me on that.
So is it the degeneration of like the chemicals, or that actual system you were laying out? What's breaking down in Parkinson's? Now that I'm just curious.
What's breaking down in Parkinson's?
No, what's breaking down when somebody has Parkinson's? Which part of it? Is it the neurons, the dopamine
dopaminergic neurons.
Yeah.
Yeah, they literally are dying. The neurons are dying.
So they're dying before they get to that ganglia tollway.
Well, they make up the basal ganglia.
Oh, so they
tollway, right? So they are key function of that toll.
So got it. So
And when
this
they
is
die, you basically get like, well, you kind of like lose your ability to really regulate the toll.
I'm just trying to wrap my head around the more unique functions and things that dopamine plays a part in, and getting a better understanding of why it's so important. Because it sounds pretty important, right? It seems like it's connecting a lot of different things and functions, like you were laying out outside of the brain. So it's fascinating.
So it's actually really important, sort of taking point, our initial point of discussion, which is like the role of dopamine in like reward, reward. I always keep drawing a blank on the name. Reward prediction. Thank you. That's what I'm on. Like a reward prediction model of dopamine, right? That's probably the biggest thing that dopamine has street cred for. Most people tend to understand dopamine as this sort of like reward. Oh, let me get that hit of dopamine, even though it's not a.
It's not actually the reward.
It's not really the hit of dopamine you're looking for. Dopamine ensures that the hit of whatever you're getting is the thing you want to keep coming back for.
Right. It's connecting that pathway of the good feeling.
Yeah.
More so than it is the actual chemical of the good.
This is actually a great segue, even though this was not the segue I was looking to make. This is a great segue into the role of dopamine in addiction, right?
Yeah.
What is the thing common things that people are addicted to, right? Illicit drugs, marijuana, possibly, gambling, alcohol, whatever, right? Let me just simply put it. Let me ask you, why do people get addicted to these things? Why are they addicted?
Probably the feeling that they get from whatever it may be.
Yeah. I mean, you perform the activity,
desired result,
a positive feeling.
Yep. I'd even call it like desired or positive, whatever that feeling is, like it's positive to you. It's the desired result.
Yeah. Now, when dopamine becomes involved, right? Let's take. Let's
use gambling.
Sure. Gambling. Is it when you win in gambling, the winning is the result, right? Winning, the result of winning is the thing, like that makes you feel good.
Right.
That feel good, right, results in a release of dopamine. And now dopamine helps connect the action of gambling to the result of winning.
Okay. So then in your brain, the path to the positive outcome is to keep gambling.
Yes.
Got it.
The dopamine is helping to enforce that pathway. It is not the thing that's physically making you feel good.
Right.
Winning is the thing that's making you feel good.
Got it.
Dopamine is the thing that's helping you connect the action to the result.
It's the bell. In our original scenario, it's the bell. Dopamine's connecting. It's making gambling become the bell.
No, dopamine, in that scenario, dopamine is the thing connecting the bell to the food.
That's what I'm saying. So like the food,
associating the bell with the food.
The food's the winning. That's the reward over here. The bell ringing is gambling, and they're connected now. So you'll keep gambling.
I'm just sort of, but I mean, I think what you're doing is you're kind of trying to compare two scenarios that don't have all the same
they don't
components.
I realized that as I was saying.
Bottom line is, right, dopamine doesn't make you feel high.
Right.
Dopamine takes the high and pairs it to the activity.
Got it.
So then when you want the high, what do?
The activity.
Look to the activity that dopamine paired it to. And that's how our brain, right? This is hardwired into us. Why? Because we don't have the ability to process every single thing we do, right? How hard would it be to enjoy going out for a bike ride if every single time you got on a bike ride, you had to mentally think through the process of riding a bike like you did when you were 4 or 5 years old and you first learned how to ride a bike, right? Mentally taxing process, right? There's a reason the phrase, it's like riding a bike, is a thing. Because that's like the most classical example of motor conditioning or motor learning.
Mm-hmm.
No, like you learn how to ride a bike when you're 5, 6, 7, 8, 9, 10.
Yeah. Well,
and then you could never jump on a bike again. But if you're 30 years old, you're probably going to be able to jump on that bike and ride down the street. Maybe you fall off once or twice initially, but then like you kind of stabilize and figure it out if you haven't ridden a bike in 20 years.
And we classify that as muscle memory.
Yeah,
right?
But it's not muscle memory. Your muscles have no memory.
Right.
They're just dumb cells. Neurons have memory. They're the root of memory. Dopamine allows you to develop the motor pathways of motor learning, right? The motor pathways that allow you to never forget how to ride a bike.
So in that, okay, now I'm starting to understand a little bit more. And if I'm getting this right, so dopamine is a key factor into your body learning how to ride a bike, essentially, right? Any activity, it opens up the pathway for that movement, and that pathway doesn't ever really close because you'll remember how to do it to some extent once you've done it once.
It becomes hardwired into motor operations, right? Well,
interesting.
It's like walking, right?
Mm-hmm.
You don't remember learning how to walk. Do you ever think about walking?
When you do, it gets really weird.
Right? Yeah. Like you don't have to engage your cortex, right? The outer part of your brain. You don't have to engage your conscious cortex to walk. Unless you're just like really underdeveloped type of person who like can't walk and chew bubble gum at the same time. Right? We all know those types of people.
Mm-hmm.
Outside of that, most people, you don't have to consciously think about walking. It's a learned motor behavior. And the way that, and this is the way our brain becomes more efficient. Mm-hmm. Right? It's almost like a computer system that's like, wait a second, I don't need to like actively pull up all the original files for this.
Mm-hmm.
I can basically create I don't know, like a zipped drive.
Think of it's a created program that's always like readily accessible, I guess. Like you've mapped it out, you've created that thing that's gonna run on the computer. You can just hit a button and it'll do it anytime.
Yeah. Basically. It's a prepackaged app.
Yeah. It's built into your iPhone. You can't get rid of it.
Yes.
And it'll always run.
And China is spying on you.
Correct.
Yeah, I mean so dopamine is very important for motor learning, right? And you can kind of start to see how, the function is not all that different, but the actual end result is drastically different, right? Between how dopamine impacts reward prediction, how it impacts motor activity, and then how it impacts addiction, and then how it impacts motor retention and learning. You can sort of start to see how like it's
got its hands in a lot of things.
Yeah, it does, right? And it doesn't actually have to be that different in terms of what it does. But when it basically it's almost like dopamine's only got so many dance moves, right? But if it picks the right partner, it can transcend all genres of dance to do different things, as long as it picks a different dance partner that just augments it properly.
That's so like what? All right. What haven't we touched on that dopamine has its hand in?
Well, I think this is a great time to dive into. There's a great paragraph. I'm not even going to try to summarize. I'm just going to read it because let's see. Let me make sure I get the right article. I think it's back here on this one, a couple of pages. So let's give credit to the authors first. This is written by these people. Where are they from? Brazil. And some private research institute in La Jolla, California.
Okay.
But this is the article I'm referencing and the authors. I think it's actually hilarious. The senior author's last name is Korea. Kind of sounds like Sydenham Korea, which is dysfunction of, or any choreic movement is dysfunction of the motor system. So I thought that was a little convenient that their last name was Korea. Anyway, old nerdy humor aside, they said describing the dopaminergic pathways and the roles in the central nervous system. The dopaminergic system plays important roles in neuromodulation, such as movement and motor, spatial memory function, motivation, arousal, reinforcement, reward, sleep regulation, attention, affect, kind of like your mood, like you can like see on someone's face that like, oh, they're sad.
Yeah.
That's what we call a sad affect, right?
Mm-hmm.
Happy affect is like someone who's like, you can see it on their face, they're sad. Someone where they look emotionless, it's what we call flat affect, right? Like they have like, they're like emotionally empty. They're not sad, they're not happy, they're empty. So that's affect. Cognitive function, feeding, olfaction, your ability to smell, hormone regulation. We haven't even really talked about that. Influences the immune system, the cardiovascular system, the gastrointestinal system, and the renal systems. In the retina, in the back of the eye, amacrine cells release dopamine extracellularly outside of the cell during daylight to enhance the activity of cone cells, which are a specific type of cells in the back of the eye.
It's the eye, right? Yeah.
That increase sensitivity to color and contrast while suppressing rod cell activity. Rods are primarily active in low light environments. So dopamine is literally enhancing your ability to like see vibrant colors in your eye. Dopamine also has other functions, including nausea. Yeah, you can actually, there's dopaminergic drugs you can give to as anti-nausea medication. Maternal and reproductive behaviors and lactation. And that kind of all fall, those, I think some of those things fall in line with hormonal regulation.
Yeah.
But
Well, it seems like it almost trains your body. Like it almost seems like it wires your entire body. I mean, you named a function that hits on like everything, which is crazy.
Like when I say like something is innate, what does that mean to you?
It's
like,
instinct.
What do you think of? It's instinct,
like an instinct,
right?
Yeah.
Would you say that riding a bike is almost like instinct once you learn?
Yeah, it's second nature, instinct. Well, I'm just using synonyms at this point.
Yeah. So dopamine is really it helps, I think, over the course of
so I almost
whatever the scheme of evolution is of man. Obviously, people have varying views. I think clearly, there's some, right? The people alive today are not the Neanderthals that we have.
Might be a few of them still roaming around.
Yeah, well, that's true. That's true. But the point is, no matter where you stand on my point in this statement is this is not a debate of like creation versus like
evolution.
I know where you're going at, right? Yeah. There's a degree of microevolution of humankind. There is scientific evidence to support that, and not just humankind, species kind. So the point of this is not to be a statement on the origin of life. I'm not getting into that. The point is to say like humankind has evolved over time. Right? Behaviors that were not once innate, right? There's encoded, biologically encoded behaviors that may not have been encoded hundreds and thousands of years ago.
I can think of one right now off the top of my head. Right. I used to work in the cell phone industry in retail stores, and
I don't know exactly where you're going with this, but I can already see where you're going to some degree. And go on. You're spot on.
What blew my mind was a 1-year-old, right? I thought they were just hitting a screen on a tablet. They were not just hitting a screen on a tablet. They knew what they wanted because they had obviously seen their parents show them where to go to get whatever video, whatever it was, and they wanted it again, right? And this is somebody who's too young to speak, to do anything, but they know that they want to hit that button to get the desired result.
So now take that to the nth degree,
Right.
That starts out as probably primarily a reward reinforcement pathway effect of dopamine.
Yep.
Now reiterate that over I mean, really, we're only in our second or third generation of cell phones and tablets, right? I mean, obviously, our generation was the last generation that basically grew up or had existed prior to the implementation of these things in society. I think every generation that's come after us basically was born with touch screens in front of them.
Yeah. At birth, essentially.
I imagine, right? Like their entire life, there's been a touch screen. So we're maybe 2, 3 more generations in? I don't know. Now, take that effect and replicate what you've just described over just a couple hundred years, even. I mean, obviously, technology is going to continue to scale. This is assuming like we don't, end up like in a war with China and or Russia and China gang up against us and like nuke the United States before we get there. Or technology advances to the point where we have like brain chips and nobody's using touchscreens anymore. That'll be the day that I'm done. I'm checking out of Earth when brain chips become mandatory. Although they are predicting the New World Order is going to attempt to put them in place by the end of the year. So
5G.
Who knows? I may be off the grid by the end of 2023 if that's the case.
We'll be doing our show from a bunker, an undisclosed location,
on an AM radio, not online.
Yep. Good luck finding us at that point.
So anyway, now imagine that effect you've described just replicated over.
Right, like that's the most simple
years.
The most simple thing I can think of, and it seems like this is
things
the type
like
of thing
touching screens, and it's going to become like biologically encoded in the brain of individuals, and that's why things that maybe were not biologically encoded a couple thousand years ago are today. Things that are generally reproductively beneficial, like maternal instincts and lactation, right? These are things that help offspring proceed and progress to in turn yield their own offspring. So there's a fitness benefit to dopamine encoding these behaviors, encouraging these behaviors. And that's why dopamine then, when you look back and you're like, wow, it affects all these different things. So that obviously we're taking a very high level view of dopamine. I don't think the scope of our show is to really get much deeper than that.
No, I think
if you're a diehard neuroscientist hoping to get in deeper, we apologize to disappoint. But if you're not a diehard neuroscientist, I hope you enjoyed this conversation because I've had a lot of fun actually. I think this was a good one.
It was eye opening. This is one of the conversations I feel like I have
and that's because dopamine is affecting your cone cells.
I feel like I have
eye opening. You can see a clearer picture now.
I feel like I have a much better understanding of what dopamine does and a little bit deeper understanding of how the brain works, which is, again, it's just so interesting to me and I enjoyed as well. So I hope everybody in the audience enjoyed.
Yeah, this. I hope everyone had fun with this one. Before we wrap up, I just want to go ahead and ask everyone to go ahead and scan our QR code. We are a nonprofit organization, and we rely on our community to support everything that we do. Yes, we live stream and we make goofy YouTube videos and we do all that for fun to support the real work, which is producing educational content, producing community service programs, and producing research that furthers our knowledge on brain and spine injuries and illnesses. If you want to be a part of all of that, scan the QR code, head over to our website. You can donate to become a member of our community. You can go on our YouTube channel and hit the join button for $4.99 a month. You can become a member of our YouTube community, and those proceeds also help support all of our nonprofit programs. On that note, let's get into a little primer for next week. We are staying on the same topic of brain molecules, but instead of talking about a molecule that naturally occurs in the brain, we're going to talk about the introduction of an outside molecule to the brain, ketamine specifically. Obviously, ketamine is used often clinically. However, kind of comes from street drugs.
So that's got some street cred as well. So.
Ketamine definitely has some street cred. So we're going to be talking about ketamine. What does it do in your brain? What are the biology of K-holes, which I actually don't know. I'm going to be reading about that over the next week to try to understand what is happening in the brain when somebody has a reported experience in a K-hole.
Special K in the brain.
Yeah. So if you want to know what a K-hole is and how your brain experiences a K-hole, tune in next week, Wednesday, 7 p.m. Eastern for the Rad and Norty Show. We're going to get into it. And if you've got questions, send them in the chat, send us an email, leave a comment on the YouTube channel, wherever you want to get a hold of us. We read everything. If you have show topic suggestions, we're all ears. We sort of just make things up as we go, and we'll add it to the mix.
Let us know. Dopamine, dope or not? Tell us in the comments.
What do you think, Josh?
Pretty dope. Pretty dope.
Pretty dope.
This conversation.
I do. Any closing thoughts from you, Josh?
I don't think so. Dopamine connections have shut off for the evening at this point.
I think that's reasonable.
But this is a great show. Thank you very much for
joining. Have a great night, everyone. We'll see you next week to talk about ketamine and K-holes. In the meantime, Rad and Norty, we're out.